deficit of the Earth's core is only 10%. So we've got significantly more light element in the metal of this experiment than we have in the Earth, meaning that we've surpassed the conditions of core formation in terms of pressure and temperature. So basically, we repeat this at a bunch of different pressures and temperatures, and then we combine this data with previously published data in the large volume press community at more moderate pressures and temperatures to parameterize how the different elements behave as a function of things like pressure, temperature, oxygen fugacity, and composition. Okay, so in this first part of the talk, we saw how accretion simulations give us information like mass evolution and provenance of the Earth and other planets. And we use high pressure temperature experiments on metal silicate partitioning to try and understand the chemistry of the core formation process. So now that we have that kind of background information, we can dive into modeling core formation in the Earth. So this is a model that we sort of layer on top of the N-body simulations in the post-processing. We assign each body an initial composition that's basically a CI chondrite enhanced and refractory elements and equilibrated at a particular FO2. And we use a more reduced inner disk and a more oxidized outer disk. Then we trace through the accretion history of anything that looks like an Earth analog. And every time it accretes something, it undergoes an episode of high pressure, high temperature metal silicate partitioning. So this first set of results I'm going to show you are assuming full equilibration of the metal and silicate at 55% of the core mantle boundary pressure at the time of the impact. So that pressure is always increasing as the planet's growing. And the temperature is pinned to be on the liquidus of the mantle. We do what's called self-consistent oxygen fugacity evolution. This is basically calculating the oxygen fugacity of the planet based on elemental partitioning between the core and mantle to ensure that you're producing plausible FO2 evolution histories. And we calculate the compositions of the coexisting metal and silicate using mass balance equations and experimentally determined partition coefficients, like the ones in the study that I showed you a couple slides ago. And then with each accretion event, we do this equilibration calculation, and then the metal gets added into the core, and the silicate gets added to the magma ocean and mixed up, and then it continues on with the next impact. So doing it like this, the resulting core and mantle compositions are an integration over a range of pressure temperature conditions. So when the Earth was smaller and it accreted something, the equilibration happened at a relatively low pressure and temperature. And when it was much larger, it happened at a much higher pressure and temperature. So our model includes a bunch of major, minor, and trace elements. Just to call out a few of interest, silicon and oxygen, we're gonna look at in terms of composition of the core. Nickel and cobalt are trace elements in the mantle that are really well studied and their behavior is really well understood. So they can serve as a sort of fingerprint of conditions of core formation. And finally, in the next part of the talk, we're going to get into hafnium and tungsten, which define an isotopic system that can tell us more about the conditions and timing of core formation. This is an example of what some of the output of our model looks like. Here I'm showing the evolution of silicon and oxygen in the Earth's core as it grows for 3 different simulations. And I chose these 3 because they each produce an Earth analog that's almost exactly 1 Earth mass, so that the variation in the final composition you see is due solely to accretion history. That is the sort of random variations in the redox state of what the Earth was accreting with time. And if we look at all of the simulations we have, we can plot them up in a histogram like this to see what is the most likely silicon and oxygen contents of the Earth's core. And what we came up with was 1.9 weight% oxygen and 5.5 weight% silicon. So what we can say more generally is that we usually see both silicon and oxygen dissolving into the Earth's core. And in almost every case, we see more silicon than oxygen. So our core density deficit is 10%. Well, if you sort of look in detail at the densities of iron silicon alloys or FeO, you'd find that the density can be matched with about 11 weight% silicon or 8 weight% oxygen. So if we have 2 weight% oxygen and 5.5 weight% silicon, we're most of the way there in terms of matching the core's density, with maybe a little bit of room for some other elements like carbon, sulfur, and hydrogen. So what about carbon, sulfur, and hydrogen? These elements are less well understood. But we recently published a study looking at the metal silicate partitioning of carbon. So this is an image of one of our experiments from 50 GPa and 5200 Kelvin. And then the same experiment as seen in a nanosims compositional map. So what we found in this study is that carbon becomes significantly less siderophile. That is, it doesn't go into the metal as much when you go to higher pressures and temperatures. So when we sort of put our experimental data into a core formation model, we found that the Earth's core could contain a maximum of 0.09 to 0.2 weight% carbon in the core. And that number is very consistent with previous estimates based on volatile depletion trends. So that's a relatively low amount of carbon compared to what we're seeing for silicon and oxygen. So it's probably not a huge player in terms of understanding the density of the Earth's core, but that does account for about 80 or 90% of the Earth's carbon budget being in the core. So it's an important reservoir to think about. In terms of sulfur, there was a very similar study done in 2017. Again, these are nanosims images of one of their samples. And they found really analogous results, that sulfur also becomes really less siderophile at higher pressures and temperatures, but not to the same extent as carbon. So when they ran their data through a core formation model, they predict about 1 or 2 weight% carbon in the core. And then that number too is consistent with estimates based on volatile depletion trends. So this amount of sulfur is fairly comparable to the level of silicon and oxygen we're predicting from our model. And just like with carbon, this accounts for the vast majority of the Earth's sulfur budget. Finally, hydrogen. Hydrogen is way more controversial than any of these other elements, and there have been no studies looking at hydrogen from very high pressures and temperatures, such as in a diamond cell. Here I'm showing a figure from Klesse et al, showing a trend in the siderophile nature of hydrogen with pressure. In that study, they report that hydrogen is not very siderophile, and that when they used a core formation model, they expect only 60 ppm hydrogen in the Earth's core. But that's a very controversial result, and there are other studies out there arguing for much more hydrogen in the core. So that's an area where we really need more work in the future. Okay, so coming back to our core composition for the Earth, if we put that all together, we have 1.9 weight% oxygen, 5.5 weight% silicon, 1 to 2 weight% sulfur, less than 0.2 weight% carbon, and maybe trace hydrogen. And if we put that all together, that gives us something like about the right density for the Earth's core. So that's encouraging. But if we want to make sure that the sort of model conditions that we're using are plausible, we always like to check things against the composition of the mantle, where we have observations we can compare it to in terms of composition rather than just density. So these are histograms for the cobalt oxide in green and nickel oxide in orange that we found in the Earth's mantle in our simulations. And in each case, this sort of shaded bar here is the actual composition of the Earth's mantle. So you can see for both of these important trace elements, we're matching the Earth on average. So that's great because that means that the model conditions that gave us plausible core compositions are also matching the Earth's mantle trace element abundances. And that gives us some confidence that our model is reasonable. So then we can go on to start playing with some of these parameters in our model. So the first one that we wanted to think about is partial equilibration of the core. So that's this idea that if the Earth accreted something that was large and differentiated, the core of that impactor might have merged with the Earth core so quickly that it didn't have time to equilibrate with the magma ocean. Geochemical estimates of the degree of metal equilibration vary something like 30 to 80%. And we know that it likely varied with things like impactor size, impact angle, etc. But here we're treating it as a constant through the entire accretion history. So you can think of it as sort of an effective average degree of equilibration. So this is the same histograms I just showed you for cobalt and nickel. To remind you, this was for the case of all of the incoming metal equilibrating at a depth of 55% of the core mantle boundary. And if we do the exact same calculation, but only have 40% of the incoming metal equilibrating, both of these histograms shift to the left. We get less cobalt and nickel in the mantle. We also get less silicon and oxygen in the core. So that now our model's not doing as good a job of matching the Earth. But interestingly, there's a pretty strong trade-off between some of these parameters. So if we do the same 40% of metal equilibrating, but do it at a higher pressure, so now 2/3 of the core mantle boundary, these histograms have shifted back to the right, so that now we're matching cobalt and nickel again, and we also recover almost the same core composition. So we see strong trade-offs between the depth of equilibration and the amounts of metal and also silicate that are equilibrating. And these are also the parameters that composition is most sensitive to. So these are important targets for future work if we want to understand the core formation process better. Okay, so in this part of the talk, we showed how matching the Earth's mantle composition implies about 5.5 weight% silicon and about 2 weight% oxygen in the core, leaving room for a little bit of sulfur, carbon, and/or hydrogen. There's trade-offs in the depth and degree of equilibration. We're most sensitive to these, and also to the accretion history, the sort of random variations in what the Earth accreted with time. Okay, so next we're gonna sort of shift gears a little bit, and we're gonna add some isotopic constraints into our core formation model to the Earth. So to start with a brief introduction to the hafnium tungsten system, we have 182 hafnium decays into 182 tungsten with a half-life of 9 million years. So that's a really convenient half-life if you're interested in core formation. You may remember from the accretion simulation that sort of, it's the same order of magnitude as planet growth and differentiation. And the other thing that's really convenient about the system is that hafnium is lithophile, meaning it tends to partition into the mantle, whereas tungsten is moderately siderophile, meaning it mostly partitions into the core. So core formation will fractionate hafnium from tungsten. So following core formation, the decay of 182 hafnium in the mantle will create an excess of 182 tungsten in the mantle relative to other tungsten isotopes. And this excess is quantified as a tungsten anomaly, which is usually defined in epsilon notation. So this is just a measure of the amount of 182 tungsten, the daughter product, in the mantle. And it's just normalized to a stable isotope of tungsten, normalized to that ratio for CHUR, which is the chondritic uniform reservoir, in parts per 10,000. And for the Earth's mantle, it has a tungsten anomaly of 1.9. So the hafnium tungsten system is sensitive both to the timing and conditions of core formation. So I'm going to show a couple of cartoons to try and sort of schematically illustrate how this works. So first, we're going to think about its sensitivity to the timing of core formation. We're going to start by considering an end-member case of very, very late core formation. So this is our cutaway of our planet. It starts out undifferentiated and full of 182 hafnium. As time passes, all of the 182 hafnium decays into 182 tungsten. And then at some very late time, it forms a core and a mantle. And most of that 182 tungsten goes into the core. That is, it goes into the core at the same rate as all of the other isotopes of tungsten. So you end up with no excess 182 tungsten in the mantle. And then on the other hand, we can think about sort of the other end member of very early core formation. So again, we start out with an undifferentiated body full of 182 hafnium. Now the core forms very early. All of that hafnium goes into the mantle. And then with time, it decays into 182 tungsten. So in this case, we end up with a big excess of 182 tungsten in the mantle relative to the stable isotopes of tungsten, which had all gone into the core back at this stage. So hopefully you can see, if you just sort of look at these final snapshots, that if we have some measure of the amount of 182 tungsten in a planet's mantle, that's going to tell us something about the timescale of core formation that it experienced. Okay, and then it's also sensitive to the conditions of core formation. So here we're just going to look at its sensitivity to the amount of metal equilibration, which we sometimes call K. And again, we're going to look at two end-member cases. So the first is complete reequilibration, which would correspond to K equals 1. So physically, what this means is that the Earth accreted something, and the core of that impactor emulsified upon impact and rained down as a bunch of tiny metal droplets that had time to fully equilibrate as they sank down to the core. So here's what that would look like in terms of the tungsten anomaly evolving with time. So initially, both the impactor and the target have increases in the tungsten anomaly with time as hafnium decays into tungsten. Then at the time of the impact, which is this dashed line here, all of these little metal droplets are going to scour out all of the 182 tungsten that's been produced in the Earth's mantle and suck it into the core. So the impact has the effect of reducing the tungsten anomaly. And then subsequently, it grows at a slower and slower rate. On the other hand, we can think about sort of the other extreme, which is core merging, or K equals 0. So physically, this would correspond to the Earth accreting something large and differentiated, and the cores merging before they had time to really equilibrate with the magma ocean. And what this looks like in terms of the tungsten anomaly evolution, it starts out the same with both the impactor and the Earth increasing with time. But now when the impact occurs, there's no drawdown from the equilibration with the metal. Instead, the mantles just mix together and you get sort of an average. And then from there, you continue to evolve up at a slower and slower pace. So hopefully what you can see from this schematically is that equilibration has a tendency of reducing the tungsten anomaly in a planet. So that's helpful because that means we can sort of look at what tungsten anomaly the Earth actually has and try and back out what degree of equilibration we would have needed to match that. Here's an example of some of our results. So here I'm showing the tungsten anomaly in the Earth analogs as a function of the amount of incoming metal that equilibrates K. So each of these data points is an average of all of the Earth analogs we formed in our simulations. And the sort of variations due to accretion history are reflected in the error bars. This dashed line here is the actual observed value for the Earth of 1.9. So in our model, we can't only change K, or we end up not getting the right composition for the Earth's mantle. So what we do is we simultaneously change the depth of equilibration. We take advantage of that trade-off we found. So that's what these numbers are next to each of the data points. That's the depth of equilibration as a fraction of the core mantle boundary. So the best match that we get to the Earth's composition is for a K of 0.4. That is 40% of the metal equilibrating. And that agrees with a previous study by Nimmo et al. And that would correspond to a depth of equilibration of about 55% of the core mantle boundary. We can see that there's a range of possible values that are allowed when you consider these accretion history error bars that we have on here. So this was for the case of equilibration with the entire Earth's mantle. We can also think about what this would look like if we equilibrated with only part of the Earth's mantle. So now here, these sort of blue-green points that I've added are for equilibration with 3 times the mass of the impactor silicate. And here, with this less silicate equilibration, we get a better match to the Earth at something like 0.9. So less silicate equilibration means we have to have higher metal equilibration. And as sort of an extreme case, we can go all the way down to equilibration with only the silicate that came in with the impactor, and that's what's shown with green. And note that it never really can match the Earth for any value of K. So what we're seeing here now in a more quantitative way is, again, that equilibration reduces the tungsten anomaly, whether it's increasing metal equilibration going from left to right, or increasing silicate equilibration going from green to blue. We can put sort of a lower bound on the amount of equilibrating silicate in the Earth. It has to have been something like 3 times the impactor silicate mass, because that's sort of where we get a match to the Earth. And if we shift to less than that, it's going to move away from the Earth. We can also say, if we look at the whole mantle case, that in the Earth, the amount of equilibrating metal K has to be at least 0.2, because that's where we're sort of just barely getting a match within uncertainty. So that's gives us a lower bound on K. And that would correspond to a depth of no more than 65% of the core mantle boundary. Okay, so then we can also use this to look at timing. So here I'm showing the tungsten anomaly as a function of the time of the last embryo accretion. That's the last giant impact that each of these Earths experienced. And now in this plot, each of these circles is a different Earth analog, not an average. And this dashed line, again, is the observed value for the Earth. So this is the case of whole mantle equilibration and K of 1. And you can see the data are sort of, crossing the Earth value for a last embryo accretion time of something like 20 to 40 million years. But interestingly, if we do the same exercise with a different value of K, say 0.2, we'd come up with these very different tungsten anomalies. And so that now we're matching the Earth's value for last embryo accretion timescales of something like 75 to 175 million years or more. And we can fill the figure in with other values of K with intermediate colors. So what we can see from this is that there's actually a range of both K and formation timescales that are allowed in terms of the observations. So when using the hafnium tungsten system to try and date core formation in the Earth, it should be interpreted with caution because a lot of these numbers are going to be model dependent. We can try and bring in some other constraints here to narrow down parameter space a little bit. It was argued, most notably by Jacobson et al., that the mass of the late veneer implies that the last embryo accretion happened at 65 million years or later, which is indicated by this white arrow. So if you believe that constraint, that now gives us an upper bound on K of 0.55. That is, if you want to match the Earth's value at this arrow or to the right of it, you have to be yellow or cooler. But we can see again that there is this complex trade-off between K, the amount of silicate equilibration, the depth of equilibration, and now also the formation timescale. But we can say more qualitative things like later formation times necessarily require less equilibration. Okay, so in this part of the talk, we saw more about this complicated trade-off between these different parameters. We constrained K to be between 0.2 and 0.55 if you buy the late veneer constraint on the timing. And that would correspond to a depth of equilibration of 0.5 to 0.7 times the core mantle boundary. And we've put a lower bound on the amount of equilibrating silicate of about 3 times the impactor silicate mass. So interestingly, these are tighter constraints on these sorts of core formation parameters than we were able to get by looking at sort of trace elements or major elements in the mantle, which is how people have historically gone about trying to constrain these parameters. And it's important to note that, again, we're treating all of these parameters as constants throughout accretion. So in each time we run the model, it only has one value of K for all of the impacts. And we know that's probably not realistic. We don't understand exactly how these parameters should be varying from impact to impact, but they almost certainly do. So you should think about these sorts of constraints as some kind of effective average over the entire accretion history of the Earth. Okay, and finally, shift gears a little bit and talk about Mars. And just to start out, I'd like to point out that this is part of the PhD work of my grad student, Matt Brennan. Okay, so why are we looking at Mars core formation? To first order, we want to know whether the core formation mechanisms are the same across all terrestrial planets. So we think we've put some constraints on them now for the Earth. Can we just apply that to all of the other planets we see, or are they going to be different? Mars is a useful planet to look at because we have samples, the SNC meteorites, as well as others. And from these meteorites, previous studies have sort of tried to back calculate what the composition of the mantle would have to be. And finally, Mars is interesting to work on right now because of the InSight mission. On the right here is an artist's conception of InSight sitting on the surface of Mars, where it currently is, and it's placed a seismometer there. And so part of its mission is to try and understand the radius of the core, and the radius is going to be related to the composition through the moment of inertia and other factors like that. So we want to better understand the composition of the Martian core in hopes that it will be beneficial to the mission. So our core formation model for Mars is pretty similar to our model for the Earth. It just differs in a couple key ways. The first is that it is currently not coupled to n-body simulations. So instead, we're just using a prescribed mass evolution. It just grows linearly with time. And that means we have not incorporated the hafnium tungsten system into our Mars model yet, although that is coming soon. The other sort of thing you have to be really careful about with Mars is that it's very sensitive to what you assume about the volatile content of the planetary building blocks. So what we've done is used a Ci chondrite enriched in refractory elements by a factor of 1.9. And that comes from the study by Taylor 2013, which was based on looking at systematics of lithophile volatile elements in Mars. And finally, just a caveat, for the Earth, we have, prototypes and other measurements of the mantle that we can compare to, whereas for Mars, we only have these sort of magmas. And so we have to compare the mantle composition that has been calculated back from these sort of indirect samples. And there's several sort of simplifying assumptions behind that. It's possible the SNC meteorites aren't representative of the Martian composition. It's possible the Martian composition is more heterogeneous, and we don't have samples of that yet. But for now, we're using the SNC meteorite compositions because that's sort of the best we can do. And so this is what that comparison looks like. Here I'm showing the concentration on a log scale of a bunch of different sort of major, minor, and trace elements in the Martian mantle. The white symbols are our calculations, and then the colored symbols are a few different previous estimates of the Martian mantle composition based on the SNC meteorites. So we can see that our core formation model is providing a pretty good match to most of the major, minor, and trace elements in the Martian mantle, which gives us some confidence that it's working. And one of the sort of first results that jumps out at us is that Mars has this really high FeO content compared to Earth, which means that the metal silicate equilibration had to have happened at a higher oxygen fugacity than it did in the Earth. Okay, and we can start to try and put constraints on some different parameters like the depth of equilibration. So here I'm showing in orange the nickel in the mantle, in green cobalt in the mantle, and in yellow sulfur in the mantle, and how these vary as we change the equilibration depth, going all the way from the surface on the left to the core mantle boundary on the right. And then we look to see sort of where does our calculated composition match the composition inferred from the SNC meteorites, and that gives us these shaded regions here. And then we look to see where they overlap, and that's this white rectangle here. So the depth of equilibration that matches all these elements, as well as others that I'm not showing here, is about 0.5 to 0.6 times the core mantle boundary pressure, which is comparable to what we found for the Earth. And we weren't exactly sure if we should expect that or not. The depth of equilibration is thought to be related in some way to the extent of melting that a body experiences. And Mars might have experienced less melting than the Earth because it may have formed from smaller impactors, but it also may have experienced more melting than the Earth because it may have formed fast enough that aluminum-26 was still alive. We find less of a trade-off between the depth of equilibration and K than we did in the Earth, but we do find a very strong dependence on our assumption about volatile content, because note that this is constrained in part by the sulfur content of the mantle, which is going to be a function of what you assume for the bulk planet. We can do the same thing for the degree of metal equilibration K, now looking at titanium oxide, sulfur, and cobalt in the mantle as a function of the amount of metal that equilibrates. And these shaded regions are where we get a match to the compositions from the SNC meteorites. And this is where they all overlap. So interestingly, we're seeing a really high degree of metal equilibration being required in Mars with a K of 0.85 to 1. So recall for Earth, we got a range of 0.2 to 0.55 from the hafnium tungsten system. So this higher degree of metal equilibration might be consistent with the idea of smaller impactors on Mars. It could also be consistent maybe with the idea of undifferentiated impactors. For the degree of silicate equilibration, which I'm not showing you here, we again could only put a lower bound on it, and it was about 20% of the target silicate, which is comparable to what we found in the Earth. And since that also is likely related to the extent of melting, it makes sense that we would get similar degrees of silicate equilibration and similar depths between Earth and Mars. Okay, and finally, we can look at the composition of the core. So here I'm showing the sulfur in this bluish and oxygen in purple in the core as a function of the oxygen fugacity that we start out at. And these shaded regions indicate the range of oxygen fugacity that's consistent with the mantle's FeO content. So what this gives us is a core that contains about 18 weight% sulfur, 0.3 weight% oxygen, negligible silicon, and about 7 weight% nickel. And so the model also gives us a core mass fraction. Now we have a composition. We can turn that into a core radius and use this to construct density and seismic velocity profiles to calculate seismic travel times that can be compared to InSight data. Okay, so in conclusion, we started out by seeing how accretion simulations and metal silicate partitioning experiments are important prerequisites to understanding core formation. There are trade-offs between the depth, timing, and degree of equilibration in the planet. Mantle and core compositions are most sensitive to the depth and degree of equilibration and the accretion history of a body. For the Earth's core, we find a most likely composition of about 6% weight silicon, 2% weight oxygen, and maybe small amounts of sulfur, carbon, or hydrogen. For Mars's core, we find 18% weight sulfur, less than 1% weight oxygen, negligible silicon, and more work coming soon on carbon and hydrogen. In terms of the degree of metal equilibration, we found really different sort of mechanisms in the Earth and Mars, a value of 0.2 to 0.55 for the Earth and a value of greater than 0.85 for Mars. In the case of both Earth and Mars, we can rule out very small amounts of silicate equilibration, but otherwise can't put too tight a constraint on that for now. And the depth of equilibration is something like 0.5 to 0.7 times the core mantle boundary on average for both Earth and Mars. And I'd like to just end by acknowledging a bunch of collaborators on all of this work and various funding sources. Thank you.
Great, thank you, Rebecca. And it's time for question. And before you ask questions, please make sure to unmute yourself so that we can hear you. And you can also raise hand in the chart. And hopefully I will, or Rebecca can notice you.
Rebecca, it's Len Sremka. Hi, how are you?
Hi.
Thanks for doing this. A great, very good talk. I enjoyed this a great deal.
Thank you.
I do electromagnetism primarily and some core stuff, and worked on the lunar core for a very long time. Tell me, does any of this tell you anything about the inner core growth on the Earth? Not just the whole core, but from the magnetic standpoint, the inner core is a big deal, right? So can you, anything from these kind of isotopic studies, tell us more about its origin and its development?
Not directly. I think the most relevant connection is in the effects of composition on the thermal structure, because these different light elements that might be in the Earth's core, they all depress the melting point, but silicon only depresses it by like 100 degrees, and sulfur depresses it by like 1200. So if we understand the composition a bit better, we can understand the thermal structure a bit better. And that might help us say something about the timing at which the adiabat would have crossed the melting curve.
All right, any more questions? So actually I have one. It looks like the Earth core has a very different trace element composition from Mars. And I'm wondering what's the major cause of that? Is it due to the different composition for their initial material, or is majorly due to the core formation process?
It's entirely due to the core formation process.
Oh,
so in terms of these sorts of refractory elements, the bulk composition is pretty similar that we're using for the Earth and Mars. Mm-hmm. But the metal silicate equilibration is happening at a much lower pressure and temperature in Mars. It's a similar sort of fractional depth, but because Mars is so much smaller, that corresponds to a lower pressure and temperature. and it's also a higher oxygen fugacity. And all of those things affect the way that elements partition between the core and mantle. And so you can end up with some really different signatures.
So a follow up on that, what's the reason for the lower temperature and pressure on Mars? Is that because Mars is just smaller than Earth?
Yeah, so I mean, the core mantle boundary of Mars today, well, it's not exactly certain, but it's like somewhere in the ballpark of like 20 GPa.
Mm-hmm.
And for the Earth, it's 135.
Oh, I see.
So we found that they both are equilibrating at, you know, something like halfway down. But for the Earth, that would be, you know, 107, that would be 70 GPa, and for Mars, that would be 10.
Mm-hmm. So, yeah, and what about the temperature difference? Is that also due to the size difference between the two planets?
Yeah, good question. So we assume that the temperature is always on the liquidus curve of the mantle. That's sort of an old school idea about core formation, that you would have, you know, part of the planet would be melted and part of it would be solid, and the equilibration would happen sort of close to that interface, which would have to be on the liquidus. And so as you go to a higher pressure along the liquidus, you are also going to a higher temperature.
Oh, I see. Gotcha. Okay, great, thanks. And I think Dave has a question here. He said it. Maybe Dave, you can just say it yourself. Hi, Dave. Oh, okay. He says it's too noisy at home, so I will say it for him. How do other elements like amount of carbon and carbon and silica affect the eutectic stories for Mars core? For example, the iron snow. Yeah, that's his question.
That's an interesting question. So a lot of the work, like this iron snow study he's referring to for the Martian core, is done, the experimental work is done on a pure iron sulfur system. And that's, you know, what we found is maybe that's not a bad approximation, but we didn't look at carbon or hydrogen. And some studies have argued that there could be, you know, non-negligible amounts of carbon and hydrogen in the Martian core. So, I mean, the short answer is that we have no idea how it's going to change the phase diagram when we throw in another element. I mean, you can try and calculate it, but really you just have to do the experiments. And to my knowledge, I don't think anyone's done them yet.
All right. And hopefully it answers Dave's question. And any more questions from the audience? Oh, so Dave still has his hand up. I'm not sure. Dave, do you have another question, or okay, he dropped his hand. All right. Okay, I think then in the interest of time, we will thank Rebecca for his wonderful talk, and hopefully you'll have a chance to visit Scripps in person in the future. And for our next week's seminar, we'll have Dr. Al Knapp to give her talk on the work she has done before she came here. And hopefully everybody will still stay tuned for that. Thank you.
Thank you.
Hi. Thank you, Rebecca.